Hello, hello, hello. All right, welcome to another week of online biology. Biology 110. Dr. E here. Going stir crazy, not gonna lie. Hope you guys are not going stir crazy. Hope you're loving being at home with mom and dad and learning biology online through YouTube. Crazy. Okay, enough. Let's get on with it. Chapter 18. So this is going to be split up into a couple different videos for the purposes of length. So I'm starting by a quick, short, little lecture about fossils. That's a fossil. Okay, fossils are old, dead things. So a fossil can be a tree, it could be a skeleton, it could be basically anything that's died and has been preserved. In the next slide or so, you're going to see some examples of fossils. And if we're being honest, you probably already have a good idea what fossils are. So let's move on to fossilization. Fossilization is the process that forms fossils, right? And so it can occur in a lot of different ways. I think we often think of fossils forming when they are formed underwater. So a fish dies and it falls to the bottom of a lake, and then over time, it's maybe buried by sand or sediment, and then that sand and sediment protects it from decomposing and getting eaten. And then over time, there's a chemical process where the molecules in the bones and even the flesh of the dead animal get converted into stone. So fossils are made out of stone sometimes, but they are basically just a copy of the dead organism. We call the collection of fossils that are in the ground below our feet the fossil record. And it shouldn't be a surprise that the fossil record is incomplete. It's only some of the animals that have died because fossilization is rare. So most of the time when something dies, it's going to get eaten or scavenged, or it's going to rot and decompose. So a fossil is only going to form when the conditions are just right. Right, and then it's also going to be selective. So in other words, not every organism that dies or every species that has died or gone extinct is preserved as a fossil. Um, and this is because the fossil record is selective. So this means when we look at the fossil record, the majority of it is marine animals or aquatic animals, so animals that live in the water. And that's because fossilization happens more frequently in the water due to the process I just talked about. We still find terrestrial animals, land animals, that get fossilized, but oftentimes it's when they get when they fall in a lake or a river, or when they get buried in ash, or when they get stuck in tree sap, or they fall into a tar pit. So there have to be fairly specific conditions for a land animal to get fossilized. And then some animals get fossilized more frequently than others. So jellyfish, just like a big, disc of slime, they do get fossilized, but not all that often. Whereas clams or mollusks, animals that have a hard shell that bury themselves in the sediment at the bottom of the seafloor or the lake bottom, they're more likely to get fossilized. So the fossil record isn't a perfect play-by-play record of animals that used to be alive. It's more of a biased sampling. But at the same time, as you'll see throughout this lecture, we can still learn a lot about the past by studying fossils. Fossils! Here's some examples. So I just mentioned mollusks that have shells that bury themselves in the sand and get fossilized. Here's a good example of that. This is petrified wood. So this is a tree that fell over, and over time it turned into stone. So you can actually even cut through these and count the tree rings and see how it grew. Pretty cool. Here's another fossil. Oh man, I just pasted this off Wikipedia, and I don't remember what it is, a bryozoan or sponge or something. That's embarrassing. But yeah, it's a fossil. This is poop. This is fossilized poop called a coprolite. So we can even learn about dinosaur diets by studying their turds that have turned into stone. This is a fish, right? And the reason I included this one is this got buried in a freshwater lake, and you can see that from this fossil, we can learn a lot about this fish's anatomy. Sometimes the fossilization process is really exquisite, and we can get a lot of detail from a fossil. So again, we can learn a lot about animals of the past, plants of the past, by studying fossils. All right, we can also try to figure out the age of these fossils. All right, and so the one of the, I don't know, most basic ways of studying how old these fossils are is to use something called relative dating. So here you're dating rock layers and fossils relative to each other. And the principle is simply that the deeper rocks or the deeper layers are older, while the rocks and fossils near the surface are younger. And this is just because of the nature in which they're deposited. So this layer of ash got deposited, and then we've got a layer of sedimentary rock, and then a layer of ash, and then a layer of rock with some trilobites. These are little marine arthropods. And then we get a layer of ash and so on. And so we might not know the exact age of these. Like these could have been deposited last Saturday and these were deposited last Sunday. We don't know. All we know is that relative to each other, these are older than these because these had to be deposited first. But what if we want to get more precise? And what if we think that maybe these, why does my mouse keep disappearing? Why are these older than these? Or we know why they're older than these. These got buried first. But how much older are they? So were these last Saturday or last June or in 1918 or a billion years ago? So we need a different technique. So absolute dating is a way that we can put actual dates on fossils or layers of rock and sediment. And in absolute dating, we use something called radiometric dating. And we're not going to get into the details of that right now, but the idea is there's these radioactive isotopes that decay over time, and they're like little stopwatches, they're little clocks. And so we can use these pretty complex techniques to get ages of different layers. So in this example, we're able to use absolute dating on these layers of ash. And so if we look at this hypothetical example, this ash layer was dated at 540 million years old. This one is 520 million years old. So how old are these fossils? I don't know. But they're somewhere between 545 and 520 million years old. And we do the same with this. So relative dating, pretty straightforward. Absolute dating, it's going to be a little bit more complex, and you have to use the right technique and to analyze only certain layers of rocks and fossils can be absolutely dated or dated radiometrically. So you got to know what you're doing here to get accurate numbers. And even then, you're usually still getting a range, but that's how it works. And by the way, we use these same techniques in archaeology. So this is another picture I stole off of the interwebs. And here we can see like a cut through of the ground below our feet. And so here's the surface of the ground. And then if you dig through here, you're going to get to 18th century, maybe an 18th century road. If you dig a little bit further, you might get medieval period architecture. Might get a pit. You can go further than that. You might get a Roman road, and then Iron Age soil, and so on and so forth. So, sorry. So, what was I saying? So, yeah, we do this in archaeology all the time. Do you ever read a news report that's like, oh, they were digging a construction site to build a new skyscraper, and they found like a Roman road, or they found a medieval sword or something? That's because over time the past gets buried, right? And so as we dig through the ground below our feet, the deeper we dig, the further back in time we go. And so we can use these different layers not only to kind of try to reconstruct what these past societies look like and what tools and resources they use, but also see how old they are in relation to one another. So we can use relative dating and absolute dating even on human objects and artifacts. All right, and so the fossil record looks something like this. So this is a section of the fossil record. And Earth's history is much longer, much older than 540 million years, but the bulk of interesting life multicellular animal life began around 540 million years ago, as you'll learn in the next slide, or not slide, next PowerPoint. And so you can see also that the various layers and collections of fossils get split up into different eras. So there's Cambrian, Ordovician. You don't need to know these. You've heard of some of these before, like the Jurassic from the Jurassic Park movie series, of which there's only maybe one good movie. And you can see that it goes all the way up to the modern period. So we're right here. So again, as we dig through these layers, if we find a fossil in this layer, then paleontologists are going to say, oh, this fossil, this animal was alive in the Paleogene, right? At least 66 million years ago. Let's see. The Earth's surface is split up into plates. And so there's lots of different plates. This image from your textbook shows some of the plates that the Earth's surface is split into. So you can see North America and much of the Atlantic Ocean is on this big North American plate. So the dry land sections are just thicker sections of the plate, and the thinner sections of the plate serve as basins, and they fill in with rainwater and water from rivers and glaciers, and these are oceans. And what's interesting is in the last 100 years, scientists have figured out that these plates aren't static, they move around. And this explains a lot of different phenomena. So it explains volcanoes, and it explains earthquakes and mountains. And so what I mean by that is if you look at the plates have these arrows, and these arrows show how the plates are moving relative to their neighboring plates. So let's look at the North American plate here. So you can see that it ends in California, and then there's this big Pacific plate. And the Pacific plate is going this way, and the North American plate is going this way. So what happens when these two plates are rubbing together? It's kind of like if you were trying to rub your hands together really tightly, one going in one direction, one going to the left, and the other going the other direction to the right. And if you're pushing down really hard, your hands might not move, and then all of a sudden, they slip. And so that's what happens with these plates. They push against each other, and then they slip ever so slightly. And when they slip, it creates an earthquake. When the plates jam into each other, look over here. Here we've got this Indian plate slamming into the Eurasian plate. You can see the arrows are pointing towards each other. And so when the plates smash together, they create mountain ranges. So mountains don't just pop out of nowhere. Mountains are formed pretty slowly over long periods of time as plates smash into each other. And when they do, the plates pile up on top of each other, and you get this big pile of rocks and dirt, and basically that forms a mountain. And we can use the motion of plate tectonics and look at mountains and look at matching rock layers and so on and so forth, and reconstruct the history of the Earth. And what you'll notice is that the Earth's continents haven't always been where they are right now. So here we are in modern day, present day, right? And this looks familiar to you. But by using this theory of plate tectonics and by backtracking where these plates have been moving over time, we can recreate the surface of the Earth over the past, in this case, 225 million years. So it turns out that 225 million years ago, all of the continents were kind of grouped together in something called a supercontinent. So you can see that North America and Eurasia were slammed together. South America and Africa were one continuous landmass. Here's India, which you saw in the last slide. So India used to be in the southern hemisphere. Antarctica wasn't always stuck at the South Pole. It was a little bit further north, and so it had animals living on it during this time. And here's Australia. And then over the next 25 million years, the supercontinent of Pangaea split up into kind of a northern supercontinent and a southern supercontinent. And this is interesting because you find dinosaurs and other critters that just lived up here versus species that just lived down here. All right, and then the Cretaceous. So as the dinosaurs were ruling the Earth, you can see that it continued to split and to fracture. So Pangaea came together, and it's kind of all the continents have kind of been bouncing off of each other and spreading out over the last 225 million years. I mentioned that we can use fossils to recreate past supercontinents. So here we are in this southern continent. So here we are going back, we're here basically. and we can not just look at rock layers, but we can look at fossils as clues. So these are different critters that were alive back then, and you can see that the fossils are found like in these continuous ranges. So this guy, we find it in South America and Africa. This one, we find it in all of these continents. And so again, we use these fossils to help recreate the past. Here's another cool example that I did. This is a awesome fish. Look at this guy. He's so cool. It's called Helicoprion. So it looks like a shark, but technically it's not. It's a fish. He's got this really weird lower jaw where his teeth kind of grow in this spiral, and they're not exactly sure what was going on. They don't really even know how to reconstruct it. It's really weird. But anyway, it's an awesome fish, and these orange dots represent where you can find the fossils. So I went to a database and I just plugged in Helicoprion, and it showed me that this is where we find, these are sites where we found the fossils. So that begs the question, why in the world do we find these fish fossils out here in the American West? Because the American West is dry desert right now. So what's up with this? Well, it turns out that 300 million years ago, which is when these fish were alive, they were swimming not on dry land in the desert, but they were swimming in this shallow sea that formed over the western United States. So just to get a sense of scale, here we are in East Tennessee, right? Here's Kentucky. And so this was a shallow sea that covered the bulk of North America. And these fish were living over here, and they died and were buried and fossilized underneath the water of a shallow inland sea. Why was the sea covering North America? Well, it was warmer at this time, and there was less water locked up in the ice caps, and so sea levels were higher, and so the sea encroached on the land. So we can use these fossils to recreate past ecosystems and past environments. So I pulled these off of Google, and this is the Silurian. So this is like what 400 million years ago. Oh gosh, let me go back and just make sure. So this is yeah, 444 million years ago. Sorry to flip through. And you can see that all the fossils we find from this period of Earth's history are aquatic, and they're really weird. We'll talk more about these in the next lecture. This is the Carboniferous, so in the neighborhood of 320 million years or so. And here we find these big forests and huge dragonflies and huge centipedes and millipedes. So again, scientists are able to reconstruct this ancient ecosystem just from the fossils. This is from the Jurassic. This is a sauropod, and we can recreate the animals and the plants that were alive during this time. Oh man, there's a Jeep in the picture. So this is a screenshot from Jurassic Park. My bad. Jeeps weren't around at that time, just so you know. Can I do this? Oh gosh. Here we go. My bad, no Jeeps. Okay. Oh gosh, how do I get this off? Okay. This is a little bit later, so this is about, I don't remember, about 50 million years ago. So this is when mammals had basically replaced the dinosaurs after they go extinct. So you can see the mammals are really weird. So anyway, this isn't just, an artist making this up. The artist used this collection of fossils from this period of time to recreate, hypothetically, what the ecosystem would have looked like. All right, and so we have all these different eras and periods. Earlier I called them eras when really they were periods. That was my bad. So earlier I introduced you to the Cambrian period and Ordovician period and so on. Well, these get grouped into major eras. So for our purposes in this class, you just need to know the three main eras of Earth's history. And those three eras are the Paleozoic, the Mesozoic, and the Cenozoic. So the Paleozoic is dominated by invertebrates. Now there's vertebrates too, but there's tons and tons of invertebrate fossils. So sometimes it's called the age of invertebrates. Sometimes it's also called the age of fish. We don't only find fish and invertebrates, but they're the bulk of the fossils from this period. So the Paleozoic is from about 544 million years ago up until about 249 million years ago. The Mesozoic, or the Middle Era, is when we find the age of reptiles, including dinosaurs, which are a type of reptile. So dinosaurs and other reptiles are the main fossils we find, at least on land, but we also find some in the oceans. And then the Cenozoic is the age of mammals. So the dinosaurs go extinct at the end of the Mesozoic, and the Cenozoic is mostly mammals, and we get all sorts of weird mammals we'll talk about in the future. Oh, same thing. I don't know, I got this on here twice. Again, just showing the three major eras and how they relate to each other. So we can date these eras relatively, right? So the fossils from the Paleozoic are older than the fossils of the Cenozoic because they're buried in lower layers. And then we can also step in and do lots of different types of radiometric dating to put absolute ages on these, and that's how they got these specific age ranges. Oh, that's it. That's fossils. So in the next video, we're going to start talking about the history of life. The next one covers the Paleozoic and the Mesozoic, and then part B will detail the animals and the plants of the Cenozoic. So stay tuned.